So what we're trying to do now is to look at understanding whether we have dark matter which comes from essentially a particle physics idea, it's an elementary particle, or whether it's more an astronomical object that we're interested in. And so what we need to do to get that is to have some form of observational test, an experiment that we conduct that determines what we're looking at. And unsurprisingly, since these regimes are very different, since the mass regime is either elementary particle 10 to the minus 20 something kilograms or astrophysical 10 to the 30 kilograms or thereabouts, we are looking at very, very different techniques for discovery. And so if we're talking about looking at machos, then the technique we can use is called microlensing. Apparently I can't spell microlensing this morning. Okay, microlensing. And the idea with microlensing is the following. I'll just insert my picture here. So if you have a universe which is filled with, say, black holes as your dark matter, then they're all over the place, they're flying around, they're not very easy to see. But periodically they're going to go between you and something in the background. So if you monitor some field with lots of stars, so say this might actually be the galactic bulge. This is a region of space which has an awful lot of stars in it. Then what you can do is you can look at all of these stars, and sometimes a black hole will go across in front of them. And a black hole, it has a very strong gravitational field, and as we saw, gravitational fields bend light. And so these stars, of course, they emit light in all directions. And say, take this light ray, for example, here. This is normally not going anywhere near us. But what eventually happens is as the black hole goes across in front here, light is curved around it. And so a light ray which would normally not come to us is focused around until it does. And then, of course, eventually the black hole moves through because these things have some velocity. And then that star stops being magnified. So what happens is, here you have the normal amount of light. Here you have the normal amount of light. Here you have the normal amount of light. And in the interim, you have much more light because of this lensing effect. So what's actually happening is you can think about this as the following. If you look at it, this is a sort of side-on view that we've got to start with. If we had a front-on view, here's our star. And here's some black hole which is going to move close to it or directly in front of it, potentially. So it's moving with some velocity here. And it has around it what's called an Einstein ring, or a lensing area, where there is a significant amount of lensing. And it's not quite as straightforward as that, but that's a sort of general idea. In practice, lensing happens at all radii. It's just that it gets weaker. And so this is something, and if the star goes inside this Einstein ring, then it is lensed, to a significant degree. And this size here is theta E. Okay, and it's going to get its light lensed. And to give you the full sort of derivation of lensing, you actually need to know some GR, which we're not going to go into, but the angle of deflection of light is given by this angle, alpha, which is just 4gm over c squared b. So this is the mass of the lens. And the lens here is a black hole. This is something called the impact parameter. You think of that as a radius. Basically, in this particular case, it's the distance between the black hole and the star at any given point. So obviously, you can see here, as the impact parameter gets smaller, i.e. the black hole gets closer in projected distance to the star, then this angle gets greater. And the reason it's called an impact parameter and not an actual distance is it's not a physical distance, it is an apparent distance. on the sky, because of course the star and the black hole are actually nowhere near each other. I should have done the star in a different colour, but the star here is in fact well behind the black hole. And in fact, the maximum amplitude of lensing happens when you're halfway between the two, but you can lens in lots of different ways. And so you can think about what's actually going to happen here to this idea of theta e, this Einstein radius, in sort of generally useful units. It's something like 4 times 10 to the minus 4 arc seconds. Now, an arc second is 1/3600th of a degree. So this is something like, 1 part in 10 to the 7 or 10 to the 8 of a degree. So it's a tiny, tiny angle. So this is why it's called microlensing. The angles are tiny. You can't actually see this beautiful Einstein ring on the sky. You just see the brightening of the star. Multiplied by the mass of the lens in solar masses to the half. This is a solar mass. Multiplied by the distance in units of 50 kiloparsec. So kiloparsec, not a megaparsec. And so this tells you something about where you look. You've got to look at distant stars. So that might be stars in the Magellanic Clouds, or it might be stars in the galactic bulge. And you're typically looking at lens masses of, a few solar masses. That's the idea. And what's going to happen is that if you think about it, the object is going to be lensed whilst it is within this theta e, this Einstein ring. So you're going to have a lensing where the amplification goes up and up and up as the angle here gets larger and larger and larger, i.e. you get more and more light because the impact parameter gets smaller, and then it will go down in a kind of symmetric way. And so you can work out what your time is. So the time a microlensing event is visible for is some delta t, and it's just d theta e for 2v, and it's roughly 90 days scaled by m over the solar mass to the half, and v in units here of 200 kilometers per second to the minus 1. And here 200 kilometers per second is the rotation speed of the Milky Way. And it's just flat because remember the Milky Way is a spiral galaxy. It has a flat rotation curve. It rises up, and it rises up to 220 kilometers per second. And then it falls away again. And so if I measure the duration of a microlensing event, I know this number is more or less constant, this 200 kilometers per second. And so I measure the duration, I get some estimate of the mass. So if I want to know the contribution to dark matter, then I need to measure lots of microlensing events, and that gives me the masses of the dark matter. And I also need to know how frequent the microlenses occur, the lensing events occur. Okay, and if I know those two things, how often they happen, if I look at some patch of sky and I see how often they happen, that gives me a route to what you call the number density of machos. I.e., how many machos there are in that bit of sky that I'm looking at. And if I measure lots of microlensing events, I get the masses. And so if I want to know, essentially, the total mass in machos in the bit of sky I'm looking at, or the volume, if you like, that I'm looking at, then what you've got to look at is n macho number times the mass And of course, they're not all the same mass, so this isn't quite as simple as just a straight multiplication, but you do n times m, and that tells you. And the punchline, which is the important punchline, is there is not enough mass in machos to explain dark matter. And perhaps at a push you can do 20% of it. So, machos, good idea. They may make some contribution, but they are not the dominant source of dark matter.